Good morning once again. So, in the last class we continue what is left in the last class. Last class we introduced what are partition of unity, and I am sure since you are taking this advanced course, this is part of the first course, so you are familiar with it. So, with this partition of unity, now we will go to the next step of patching. Okay. Suppose T, suppose you write omega is equal to unit. Of course, I do not make the index at all the time, but you can write it. Omega is equal to omega I, and T I is in a distribution in omega I. Okay. So, you can want to do that one. Okay. D prime of omega such that I said it in intersection. If there is an intersection, it should match, such that if omega I intersection omega j is non-empty, then T I, you can restrict T I, which you are already see how to localize it. So, you can restrict to omega I in omega j. So, it is something like that, right. So, you have omega I, this is omega I, this is omega j. So, you can restrict T I to the intersection, and this is your omega I intersection omega j. Okay. So, this should be the same as T j, you can restrict that also, omega I intersection omega j. Then this is the theorem. So, you can call it a theorem if you want. Then there exists a unique, this is important, unique T in D prime of omega such that T is equal to, so you can restrict that T restricted to omega I is your T, okay, Ti. Okay, this is for all. Okay. So, the proof is very easy, so almost what you have to say. So, you have to define T. So, phi in d omega, so you have to let phi in d omega and phi I the partition of unity, partition of unity, any partition of unity. Now, unity, there will be many partition of unity, okay, it need not be unique. Partition of unity is not unique, but our distribution T will be unique. You have to prove the uniqueness. Also easy, partition of unity corresponding to omega I. So, that is how you say. Okay. And then phi phi, so you define, so that your definition T phi is equal to summation of our I T I of or phi phi or T j, let me use phi phi j, anything is fine. Okay. So, if you want the uniform notation, let me give uniform notation. Okay. Phi I j omega j. Okay. There is nothing wrong, I am just writing T phi phi. Note that phi phi support of phi phi j is in omega j, keep that in mind. So, this is well defined. Again, due to locally finite partition, this will intersect, this will be finite, okay, because it can intersect only finitely minimum. For other things, T of phi phi j will be 0, as finite as T phi phi j is 0 except for finitely many, except for finitely. Yeah, the follow these conditions immediately. So, you have that one. Okay. So, you have to prove continuity is easier, right? Everything you have to prove continuity. You have to prove that continuity. So, if phi m, let me not use, let me not use phi m, because you already have the partition of unity. If psi m goes to 0 in D, that implies psi m as m tends to infinity, write down your index properly. Then psi m phi j converges to 0, this is in d omega, you can say that in d omega j for all j, this is as m tends to infinity. So, for all j, that will imply T j of psi m phi j, because T j's are continuous, goes to 0, that will imply the summation. Summation is again finite, so you do not have to worry. You can say that T of psi m, that is nothing but summation over T j of psi m phi j over j, this will go to 0. So, continuity is obvious. Okay, that implies T is in d prime of omega. Okay. So, this is one thing you want to. Second, to prove okay, T restricted to omega j is equal to T j, you have to prove that. Okay. So, or Ti, whatever it is, which one I want to take it, maybe for summation, that is why I used j there. Okay, T restricted to omega I is equal to Ti. Okay. So, what do you do? So, you have to show that, so take let phi with in d of omega I, that is what you have to prove, d is in omega I. Then for any j, that is what you have to take it, you want to prove that T restricted, if the support is in omega I, you have an extension, that is what you get it. Okay. So, you want to prove that it is restricted. So, for any j, phi j, phi has support in d omega I, phi j has in support in omega I. So, this belongs to d omega I intersection d omega j. Oh, sorry, d omega j. So, now and then that immediately implies, because it is in both omega I and omega j, and Ti and Tj, j is fixed now. So, T I and Tj are the same, for j is fixed, for anything phi j has that one. So, Ti of phi j is same as Tj, because it has support in that, phi j is a fixed quantity. Okay. This is true. Okay. Ti of phi j is equal to T of phi j. Therefore, that implies your T phi, this is what you want to show, is equal to summation over j of Tj of phi j by definition, that is it. Whichever has summation thing, you get this one. So, that is same as summation again j, this is j, Ti of phi j. Now, Ti is independent, that is what you can take it T outside now, summation of j phi j. So, it is a working index correctly. Okay. And but then Ti, Ti is same as T. Ti, this is nothing but Ti, and this is your phi, because this is over summation. So, once you have summation of Ej is equal to 1. So, this is nothing but your phi. So, okay, Ti of phi, and T phi is equal to Ti of phi for all phi in d omega I. Okay, that is it. The third part is uniqueness. 3, uniqueness. It is also similar proof. Nothing, actually these are all exercises, but probably learning it for the first time we will do it. If, because it can give a different partition of unity and it can give you another S, which if S is in D prime of omega with S phi is equal to Ti of phi for all phi supported in domain of omega I, then you have to show that T phi equal to S phi. That is all the property. If you have another distribution, the only property is this one. So, if you have another distribution which gives you the same Ti, and then T phi equal to S phi. So, now use, so you again take a psi, take to see this, take psi in d omega, then you can write it as psi is equal to summation psi phi I, because phi I is the partition of unity. I am using that. Psi phi I, that implies T psi equal to summation, by definition, not by definition, psi is this one, this is summation. Oh, why did I do this one? Okay. C phi I. So, T of psi phi I, okay, is over I. But then T of psi phi I is equal to T psi phi I, as psi phi I has support in, support of psi phi I is in omega I. Okay. So, this is nothing but Ti psi phi I. But then Ti of psi phi I, this is also with the true. So, you see S is also the same thing. On omega I, it coincides with the Ti. So, this is same as summation over I S of psi phi I. You see, Ti is same as S on functions defined on omega I psi phi I, and then you can take it S outside. So, you get S phi. So, it is a almost a immediate proof. So, you can actually patch up everything S of psi, I think. Okay. So, this is S of psi phi I is S psi, okay, because we are so used to phi. So, we keep on writing phi, but we used psi. So, you can patch them together. So, this is an important thing to get global solutions later. Okay. So, how to patch, and partition of unity is a great help of unifying. You get global solutions to that. Now, let me do my singular support definition. Singular support. Okay. This is important again. You recall if the support of a T. Support of T is the complement of a open set, largest open set where T vanishes. So, you have looking for open sets where T vanishes, that means T does not contribute, T equal to 0. So, you are locally open sets you are identifying with 0 function, but quite often if the support will not be able to identify 0 function, but there will be regions of T for which T can be identified with a function. Globally you may not be able to identify with a function. For example, you take a Dirac delta. You cannot identify delta with a function, the distribution. But if you remove a neighborhood of the origin, outside it is 0. Okay. So, there you are identifying, but certain places it is possible that T can be identified with a function more in particular you will be able to identify. That means the solutions of PDE may be defined in a very general setup, not as function, but there will be lot of regions where that such things can be defined by C infinity function. So, the singularities where you cannot identify it with a function may be some areas, and only that areas we call it the singular support, because that is where the singularity happens in the thing, and this is again crucial where your solution have singularities. Okay. So, with that so let me give you the definition. So, it is the same thing. Okay. Let T is in d prime of omega, then the singular support, we write it singular support of T is the complement of the largest open set, complement of the largest open set where T is C infinity. That means on that open set your T is given by a C infinity function. T is C infinity. Okay. So, so immediately you know that immediate corollary is singular support will be small. The support is a complement where T vanishes, which is a C infinity function. So, the where it coincides a C infinity function will be bigger, the open set will be bigger, the singular support will be smaller. Okay, singular support of T is contained in support of T, and for all the support of Dirac delta and its derivatives same, singular support, immediate verification delta is equal to 0. But then you look at the Heaviside function H, Heaviside. Function H. What is H? Let me recall. This is 0 here, 1 here. Right. This is your H. Here the support of H is equal to the closed interval 0 to infinity. But whereas if you remove a neighborhood here, any neighborhood here, all other places, each open set, this open set C infinity, of course this is disconnected, you can say that in the union it is a C infinity function. Yeah. But the so singular support of H is equal to 0. You see the support and singular supports are different. So, you can calculate the singular supports given. Okay. So, our main part then we will make some remarks. I am going to state the local structure. I will not prove here, I will only state now. If you want, you can look into the books like Barrow's net or something like that. Barrow's. You can book other books also. Other books, maybe Rudin and other books. Local structure of T. So, let me just state the theorem. and if you want a proof you can look into the books. It is not that very difficult, but it may take some time. So, let T belongs to locally, you know that a integrable locally integrable function gives a distribution, and once you take a locally integrable function, its derivatives need not be locally integrable, it may not even be a function, but the derivatives are also distributions. So, essentially telling that locally every distribution is basically some derivative of some locally integrable function. That is what it says. This you can get it only locally, but if that has a compact support you get a global representation. That is obvious, because outside compact support T has no issue. So, inside the thing you can write is a global result. So, and T belongs to d prime of omega, and omega naught is compactly. So, this notation you are, this is open, and omega naught bar is also, omega naught bar is also contained in omega. So, you can't go to the boundary. So, that is a thing. How do you take? Okay. Then there exists f belongs to L infinity, that is integrable omega naught m greater than or equal to 0, such that your T is some derivative of something. So, we do not know m n okay, dx1 power m1 m etc. You can write it maybe in different ways. So, okay. So, no, not necessarily even summation, I think this is not necessary on omega naught, some derivative. Okay. Okay. In fact, you can further integrate, you can say that it is a derivative of some continuous function. You can, because locally integrable function, take it and then you will get a integrate, you get continuous functions. So, you will be able to write the derivative of a continuous functions. Okay, such things can be done more than like. In general, that is true. Okay. In general, one cannot have a global representation. One cannot have a global representation. But if T is compact, then T can be written as, some summation d power alpha globally for some m again of various functions, where in omega you have that one. So, you have keep that, this need not be, even if f alpha is nice functions, d power alpha is still. So, you are not writing that T as a compact support. Okay. Then T is equal to in omega now. So, meeting that we are not writing T as a function, it is a derivative of functions. Okay. Nice functions. Okay. With f alpha continuous and compact support. So, do not try to misread that T can is a function all the time locally. No, you are not saying that T is a local, every local thing T is a function. We are not claiming that, it will be derivative. The derivatives like dh is delta, and delta is not a delta is not given by a function in compact support. With this we are more or less finished in the distribution theory, finished in the sense that in this course, but I will do few things if I some comments or what I say, some results in for distributions. So maybe you can say remarks or comments, and not actually it's remarks. You can say that comments, some results before completing distributions in R. So you can say something more in distributions. Can do for generalizations of these results also, but this, with connecting with your familiar notions of primitive, okay, primitive concept of distributions in D prime of R. Okay, some comments about that thing. So it start with a definition. Same definition what you are familiar with the function. You want to define as much as possible. We say T belongs to D prime of R is a primitive of S as a distribution again. So, same definition like function if dt by dx equal to, so we are dealing with one dimension, is equal to S, that is all. So, the immediate theorem in the sense that of course you need to give a proof for that. Every, so you may ask the existence. So, basically you are trying to solve this problem, okay, dt by a, that is what your integral calculus in functions. So, you are definitely telling that integral calculus for your distributions. Every S in D prime, so even if I do not write R, it is we are dealing with R, has infinitely many primitives, has infinitely, which you know in the case of function, many primitives, and two of them differ by a, two of them differ by a constant in the sense of distribution, differ by a constant, okay. That is if dti by dx equal to S for I equal to 1 to 2, then t is equal to t1 minus t2 is given by a constant. I will not write in general, but I am telling that means when I given by a constant, where C is a constant. So, in particular, especially, okay, anyway this is an exercise you would have done it by now. If dt by dx equal to 0, that means 0, then t equal to Tc constant, you see. So, the same thing f prime of x equal to 0 in an open set, then f is a constant here distribution even in the distribution. So, you are basically solving that equation, okay. So, let me make some, yeah, so this is the thing. So, we will start with thing. If some interesting things in the process of the proof, if phi psi, maybe you are already used this, but since it is important, is also if you have not done that last problem dt by dx equal to 0, you would not have seen this one, if you have seen otherwise, okay. And phi equal to psi prime, so these are very general comments, okay. Phi is equal to psi prime, that implies integral say minus infinity to infinity, phi is equal to integral minus infinity to infinity psi prime, and since psi has compact support, that is equal to 0. So, what conversely, so that means the question is that given two compactly supported function or given a compactly supported function, can we write it as a derivative of another compactly supported function. So, this indicates that this is a necessary condition. So, you may need minimum that condition, and is saying that this is the exact condition. So, if you want to write a given phi, if you want to write, so given phi in D of R, so can we write, can we get phi is equal to psi prime for psi in d omega d of R, you see. And what the above thing is in it is not always possible, you may need minimum condition, is says that exactly that condition is enough. So, a natural choice for this is a kind of an antiderivative, a natural choice is the differentiation, natural choice. So, I am making some slightly more way, every function have. So, natural choice for any phi, you define psi x equal to choice, define some psi x equal to integral minus infinity to x phi x t dt, you see. So, that will imply if since phi has compact support, psi is C infinity. It will not have compact support in general, okay, because but on the okay, it will have, because phi has a compact support, it will not imply psi compact support after that. So, on the other hand, if you have these conditions, you can indeed get that one. Okay. So, this is a basically a necessary and sufficient condition, okay, necessary and sufficient condition for this one, to have that one. But more generally, so even if you do not have that condition, you can write every phi more generally. Choose, the problem is that you do not get, so we make compact support by multiplying by a compactly supported function d of R, but it does not, you do not want any integral value to be given. So, you normalize it, dt is equal to 1, and let chi is equal to, now you see integral, this may not be 0, you see. If this is 0, you do not have to do further. If integral minus t to d phi t equal to 0, you will get already this one. So, this may not be 0, and let me, sorry, yeah, nothing wrong, I want this to be for some other. You call this lambda, not chi, this number. If lambda equal to 0, you have that representation. But then more generally, what you have, define your chi is equal to phi minus lambda phi naught, lambda is this constant. Okay. So, that, so now integral of chi, this immediately implies is equal to integral of phi minus lambda integral of phi naught, lambda is a constant. Okay. So, this phi naught you made it a compactly support. So, you see this is in d of R, you get it, and integral of chi, this is nothing but lambda, the other one is 1. So, you have 0. So, chi is equal to 0, that implies chi is equal to psi prime for some psi in d of R. So, that what all this tells you, that one. So, you have this basically implies, then from here you see you can write your phi in this form, lambda phi naught plus chi, where plus chi, where chi is psi prime, where chi is equal to psi prime, you see. So, you have that thing to get it. So, maybe I will spend few more minutes. So, you have this representation always. So, what we have this that immediately, so you can, so if some gaps are missing, please do it, I will try to do it. So therefore, so we are coming back to the problem of primitive. So dt by dx, so I use the same notations. So dt by dx equal to s if and only if your t phi, so your t phi chi is equal to t psi prime, that is equal to minus dt by dx psi, that is equal to minus s psi. So you have this one. So if you have t chi is equal to minus s phi, you have that relation. Okay. So if s is in d prime of r, let me do it slightly quickly, d prime of r, define now, I want to solve the primitive problem, okay, primitive problem. Define, so you have every phi, define for phi in d of r, you have that representation, phi is equal to what is that representation, let me recall. Now phi has this representation lambda phi naught, of course it depends on your choice of phi naught, that is material, okay, chi, where chi is psi prime. Okay. So you have that the thing, you define for this one your t of phi is equal to some lambda, the same lambda, some constant, any constant arbitrary you can choose it. So you get different things. So that is why it is not unique. So and that is a constant you will come. Lambda c, so t of chi is minus s I. So you have that property. Okay. So that is exactly if dt by ds has to be this one. Of course, there is some verification we like in particular. If phi is equal to chi, happen to by chi, that is equivalent to saying that your lambda is equal to 0. So for some lambda for your integral value 0, so you immediately, so chi is equal to phi equal to chi, then chi is equal to psi prime immediately, and then that case, in this case lambda is equal to 0, that is the meaning of lambda equal to 0, and d of chi, that is t of phi, lambda is equal to 0. So there t of chi is equal to nothing but minus s I. That is precisely the condition dt by dx is equal to, yes. So you can solve it. Okay. Of course, one exercise which you may need to prove is that t is defined in slightly different way which you have not seen, but so you have to show the continuity of t. Exercise is continuity of t, not that it is difficult, but you have to see, but corresponding to phi k, phi m, you will have lambda m and all that, and you have to work out that one. Okay. And the other exercise also you can prove uniqueness, okay, that is trivial uniqueness, okay, exercises, because if t ti by dx equal to 0, no, s the same as, okay, that will give you your d by dx of t1 minus t2 is equal to 0. From there you can derive t1 minus t2 is equal to t of c. Okay. And you can repeat this one in the sense that if you generalization, you can do generalization. Okay. You can solve the second order. So if d square t by, for example, if dt by dx is equal to 0, t is a constant, and d square t by dx square is equal to 0, then you can put s equal to dt by dx. You see, you can put dt by dx is equal to 0 s, and that will imply your ds by dx is equal to 0. That will imply s is a constant, say c1, s equal to c1. S equal to c1 means tc1, the corresponding this one. That implies dt by dx equal to s, and d by dx of c1 of x is equal to s. Okay. So, you have two distributions t and c1x giving the same derivative s. So, by our uniqueness, that will imply your t is equal to c1x plus some constant c. So, you see. So, it is a so d square t by dx square solution is nothing but your thing, and like that you can keep on doing, and then you can ask for the mth primitive or primitive for order m. So, whatever you want to do. So, I will stop here, probably something. So, I thought about the, you can also talk about some absolute continuity notion. Exactly you do it. If it is an indefinite integral of a function, then you see that that function, and there is an absolute continuity notion for functions. So, you can start with a distribution, maybe give it as an exercise, and if dt by dx is a locally integrable function, then t can be realized as an absolutely continuous function. So, exactly what you do here. Okay. That is a Lebesgue theory. So, you have an fx by an integral of local integral, this function is absolutely, that is a notion of an equivalent condition derived for the absolute continuity, okay, which can be done for your distributions also. So, with this lecture I will stop about the lectures on distribution theory, and in the next set of lectures you will see how we use this one and introduced Sobolev spaces and all that. So, we will have a sequence of a set of lectures on Sobolev spaces. Thank you very much.